My name is Zolt LeVay. I'm an imaging team lead in the Office of Public Outreach at Space Telescope Science Institute. There are hundreds of thousands of images. My part of this operation is to convert Hubble data into pictures.
347 miles above us is the Hubble Space Telescope. A cross-section reveals a fragile curved mirror protected deep inside a tube as big as a city bus. Up here, Hubble avoids the distortion of light by the atmosphere as it captures starlight, producing stunningly beautiful views of the cosmos. Some 4,000 teams have sought precious time on the 2.4-meter mirror and advanced digital cameras, pointing Hubble to the deepest regions of the universe, taking snaps of galaxies, nebulas, star nurseries, and violent supernova explosions. All colorful. But actually, Hubble images start off as black and white photos. The telescope's camera takes 3 exposures for every shot, each time with a different filter. On Earth, astronomers overlay filters of red, blue, green, infrared, and ultraviolet. Mixed together, they reveal the beautiful full-color versions of the heavens. Most of the space images are processed here at the Space Telescope Science Institute in Baltimore, Maryland, in the United States. Zolt LeVay leads the team, turning observation data into images.
This image was made using 5 different filters with the visible light camera, a wide field camera 3. These are the individual filters that we use to construct this image. This is the image that was taken in the light of hydrogen. The most important feature of this, in this case, is the stars nearly disappear, because what we're looking at is the light that glowing hydrogen gas is producing, and the stars are producing relatively less of that kind of light. Here's light that's nearly the same color, a range of colors, red colors, and now we see the stars much more prominently. So here's the hydrogen image in the red light of hydrogen. Here's the near-infrared image, also red light. Here's the yellow-green color in visible light. So then we apply color to these, and then when we put those all together, we get the full color image. What we see is mostly gas and dust. There are dark areas where there's either no gas or the dust is absorbing the light from behind it. There are brighter areas where the gas is glowing. There's also a lot of stars here, and in the process they're blowing a bubble in this material. You can see this cavity, and it's also pushing against that gas, causing it to be compressed, and new stars are being formed. This is a cluster of galaxies called Abell 2744. This is part of a large project with the Hubble Space Telescope and other observatories called Frontier Fields. The Frontier Fields project is hoping to probe as deep into the universe as is possible with the Hubble Space Telescope.
Hubble's deep fields and frontier field observations can see back in time by means of gravitational lensing, which boosts the light from more distant galaxies.
The gravitational lens is a feature of the actual galaxy, the galaxy cluster itself. The mass in the cluster, the galaxies and the intervening material, distorting the light that's coming from behind it. We've seen numerous images of galaxy clusters, and we see these wonderful forms of the effect of the gravitational lensing, the bending of light by the mass in the cluster. These exposures are hours, many hours, in many different filters. What really happens is that the noise level goes down. As you build up more and more exposure, the noise level gets relatively lower compared to the signal in the faint source that you want to look at. This image is very exciting because I feel like you're looking through the whole universe. So we're seeing stars in our own galaxy, which are relatively close by, We're seeing this cluster of galaxies, which is millions of light years away, but through that cluster, we're seeing things that are immensely farther away, billions of light years away. And so we're just seeing this whole range of distance, this unimaginable range of distances. This is one of my favorite images from the Hubble archive. It's called the Sombrero Galaxy. Astronomers would call it M104 from the Messier catalog. And seeing it in books, there's a very famous book called the Hubble Atlas of Galaxies. And the Sombrero Galaxy features prominently in there as a prototypical example of this type of galaxy. So this object has been studied for a long time by a lot of astronomers, and quite a famous object. This is a spiral galaxy, so similar to our own galaxy, where there's a disk of material that's made up of stars and gas and dust. Along with that disk, it's a fairly flat, round disk. There's what's called the bulge, which is this sort of bright, hazy, it's all made up of stars, in a more spherical arrangement around this galaxy. We took 6 separate fields to build up a mosaic of this galaxy because it's relatively large on the sky. It's a relatively close galaxy, and that's why it's fairly bright and easy to see. There's a fair amount of work that went into this one to stitch together the separate images. We actually did that by hand rather than use a piece of software to stitch it together, but it worked pretty well. I think the result shows a very spectacular result of a very iconic astronomical image. In overall broad structure, we would see something like this. If we could get far enough away from our galaxy and look back at it, we'd see something very similar to this.
Astronomy textbooks typically present galaxies as staid, solitary, and majestic island worlds of glittering stars. But galaxies have a dynamical side. The Hubble Space Telescope conducted 59 views of colliding galaxies, gathering the largest collection of Hubble images ever released to the public in 2008. This illustrates how galaxy collisions produce a remarkable variety of intricate structures in never-before-seen detail. Zoltan Levay looks at a few of the images in the collection.
Here's a small collection of some interacting galaxies that Hubble has photographed. And you can see that they come in lots of different forms. And basically the different forms are snapshots of an event that's unfolding over millions to billions of years. There are a few examples. For example, in this case, the galaxies, you can see that they're relatively close to each other, but they're far enough apart that there's not too much going on. If we look at something more like this, we see they're much closer together, and maybe you can start to see some disruption. And this is one of the things that people are finding that happens in galaxy collisions. People are able to make simulations or models of galaxies in the computer, and you can make a model of 2 galaxies that come together based on fundamental physics. And you can compare what you see in the model with actual data, with actual images. And these are comparisons of this particular model of these 2 galaxies interacting. And at certain phases of that interaction, we can compare them with actual Hubble images and see that the match is almost uncannily similar. You can see that now the shapes, whereas they probably start out more regular spiral galaxies like that, they're now highly distorted. The arms have been stretched out because of the gravitational, the tidal forces. Some of the material will be spread out over very large distances. I mean, we're talking, in some cases, 1 million light years across.
Astronomers estimate that only 1 out of 1,000 galaxies in the nearby universe is in the act of colliding. However, galaxy mergers were much more common long ago, when they were closer together, because the expanding universe was smaller. NGC 6670 is a pair of overlapping edge-on galaxies. Scientists believe that NGC 6670 has already experienced at least one close encounter and is now in the early stages of a second. The nuclei of the two galaxies are approximately 50,000 light-years apart. NGC 6670 glows in the infrared, with more than 100 billion times the luminosity of our Sun, and is thought to be entering a starburst phase. For all their violence, galactic smash-ups take place at a glacial rate by human standards. Timescales on the order of several 100 million years.
When they collide, the individual stars don't necessarily bump into each other. Occasionally you might have a few stars bumping into each other, but it's the more amorphous material, the gas and dust clouds and the other matter within a galaxy that interacts gravitationally. And that's where all the interesting stuff happens. In fact, people think that it will happen to our own galaxy. We have a neighboring galaxy called the Andromeda Galaxy. It's 2.5 million light years away from us currently, but it's actually getting closer all the time. And people think that it's on a direct collision course with the Andromeda Galaxy. And in a few billion years, we're actually going to turn into one of these interacting galaxies. And the galaxies will kind of dance around each other and hugely distorted, but ultimately the gravity pulls it all in together. And as you can see, they end up being this smooth elliptical galaxy. This is our future. And presumably, depending on how things pan out, we may not actually feel that anything's happened. Our sky will be dramatically different. We'll see this galaxy approaching us closer and closer and closer, if we could live for billions of years, that is, and if the sun would last for billions of years more. But presumably, individual stars and planets wouldn't be too much affected by this. You better be prepared, because it's only going to be a few billion years till that happens. But indeed, our galaxies will collide with each other and be highly distorted. My favorite would have to be this guy, just because it's so unusual. You don't see any spiral structure, really. An enormous amount of star formation has gone on in this galaxy, and that star formation was triggered by this galaxy interaction. So the gas from the two galaxies collided and got compressed, and there was a huge burst of star formation as the galaxies collided.
One of Hubble's best examples of star formation can be found in the Carina Nebula. Located in the Milky Way, seen in the southern hemisphere, around 7,500 light-years away from Earth. Here are towering pillars of gas and dust of collapsed stars, now the home of new star nurseries.
It's all gas and dust, but that gas is being eroded away, evaporated away, but it's also being compressed by this wind and by this radiation that's coming from these stars. And it's being compressed so much, you can see that a lot of these tips of these pillars look like they're just a lot denser than the other areas. And it's being compressed so much that new stars are being formed deep within these pillars. These are jets of stuff that's being shot out across interstellar space, several light years across space. And that's what we're seeing here. And they're running into material that's already there and producing these little bow shocks, like a ship plowing through the water. And so we know that there's new stars formed down in these tips of these pillars. And there's probably many more that we can't see that are not producing jets at this particular time.
Hubble conducts observations of near and far objects, some in our solar system, such as planets, and others much deeper in space. And sometimes Hubble observes a changing universe.
This is an image of an object called V838 Monocerotis, what we call V38 Mon. This is actually a very unusual object in astronomy. This star had an outburst that didn't last very long in astronomical terms. What we're actually seeing is the light shining on the material around the star, propagating through that material. This material is not expanding. A pulse of light is expanding around this star through the material. This is a progression of images taken over a period of several months from May of 2002 through September, October, and December. That's an almost unprecedented thing to see in the universe, where things are so large and timescales are so large that over even a human timescale, we hardly ever see anything change. You're seeing the structure of this material in 3 dimensions, and people are actually building 3-dimensional models based on these observations of this pulse of light traversing through this material. It's unprecedented to see this kind of change on this kind of timescale with this amount of detail.
The NASA ESA Hubble Space Telescope continues to surprise us with new and remarkable images that show how our universe is changing over time. In 1997, it imaged 3 magnificent sections of the Veil Nebula. Now, a stunning new set of images from Hubble's Wide Field Camera 3 captured these scattered stellar remains in spectacular new detail and reveal its expansion over the last years. Deriving its name from its delicate, draped, filamentary structures, the beautiful Veil Nebula is one of the best-known supernova remnants. It formed from the violent death of a star 20 times the mass of the Sun that exploded about 8,000 years ago. Located roughly 2,100 light-years from Earth, in the constellation of Cygnus, the Swan, this brightly colored cloud of glowing debris spans approximately 110 light-years. Despite the nebula's complexity and distance from us, the movement of some of its delicate structures is clearly visible.
Hubble took images of the Veil Nebula in 1997 with the Wide Field Planetary Camera 2. Since then, servicing astronauts visited Hubble during a Space Shuttle servicing mission, replaced Wide Field Planetary Camera 2 with the new instrument, Wide Field Camera 3, which has better resolution, better sensitivity, slightly wider field of view.
Flight PDRS. Go ahead. The telescope's released. Okay, thank you.
And so we've now revisited the Veil Nebula, same region of the Veil Nebula, with the newer camera and taken even better pictures. This is a view taken by a telescope on the ground, showing the whole Cygnus loop. And another telescope on the ground took this detail. Some people call this the witch's broom. And then Hubble zoomed in on this small part of the witch's broom to show us these very fine details with very nice resolution.
These new Wide Field Camera 3 images cover just a tiny fraction of the nebula's outer limb, located on the west side of the supernova remnant.
We're able to show the change between the 1997 image and the 2015 image. And you can see these very small features are shifting in their position. That's not so much the material moving, it's this shock wave from the supernova blast moving through the material and exciting that material to glow in different places through that interstellar material. It is the result of a very violent event, among the most violent events that happen in the universe. A single supernova explosion can outshine all the other stars in a galaxy. It can produce that much light.
Astronomers suspect that before the Veil Nebula's source star exploded, it expelled a strong stellar wind. This wind blew a large cavity into the surrounding interstellar gas. The blue-colored features outlining the cavity wall, appear smooth and curved in comparison to the fluffy green and red-colored ones. This is because the gas traced by the blue filter has more recently encountered the nebula's shock wave. Hidden amongst these bright, chaotic structures lie a few thin, sharply edged, red-colored filaments. These faint hydrogen emission features arise after gas is swept into the shock wave, which is moving at almost 1.6 million kilometers per hour.
The remnants are spectacular and beautiful, but very ephemeral. On a cosmic timescale, this may last for a few thousand to a few million years, but that's a blink of an eye in a cosmic timescale. The Veil Nebula, or the Cygnus Loop, is astonishing. I mean, just looking at it, the wider images on the sky, I mean, it's hard to find a place to look. It's kind of like going to some great national park or something, like the Grand Canyon. You don't know where to look because everywhere you look is a spectacular view. Well, the Cygnus Loop is the same way. You zoom in on any part of the Cygnus Loop, and it's a spectacular, different place you're looking at. The structures are varied, the colors are dramatic, and it's just an amazing thing to explore. I wish we had enough time on Hubble to look at the whole thing, but we don't.
Since its launch in 1990, worldwide, astronomers have captured 1.3 million observations. Their images have taught us about the size and age of the universe, determined how planets and galaxies are formed, spotted thousands of galaxies in pitch-black regions of space, and have allowed us to witness violent supernovas and pillars of creation. Time on the telescope is tight, though. Astronomers have seen the tenacious Hubble already last beyond its 15-year sell-by date, with 5 servicing upgrades. But every day, it's being slowly dragged back toward Earth by atmospheric friction. With no shuttle to push it back up, it will crash back to Earth, or be deorbited. Hubble is expected to be operational beyond 2018, when the next generation James Webb Telescope comes online. In the meantime, there are thousands of images yet to be processed. Zsolt LeVay and the team at the Johns Hopkins Space Telescope Institute have plenty to keep them busy to the next century.